this is another math talk, but this is going to have a lot of drawings in it. You yourself will have to draw. So this is Vijay Ravikumar from CMI. He's going to talk about geometry of vision.
Yeah, so today we're going to look at the geometry of vision. And we'll see what that means as we go along. But to begin with, I wanted to look at a few paintings, a few drawings and paintings that people have done over the years. So here's an old painting. Probably you haven't seen it, but it's from Italy in 1426. People often credit this as one of the first paintings that used linear perspective. So basically there was a new technique that a few Italian artists discovered. And soon after they discovered that technique, more and more paintings started using it. And this is one of the first. So this is called the Tribute Money. It's a religious painting, and it's from 1426. You can see that it looks somewhat realistic compared to much older paintings. We'll see in a second how some of the earlier paintings looked. Here's a much newer painting that also uses linear perspective to give a sense of space and depth. This one's from 1914, so not very old at all, from France. And here's another painting, somewhere in between, from 1665. This is also from France. And this one uses it also uses linear perspective combined with a very, very precise and careful, almost photorealistic type of brushwork. So it looks almost like a photograph, but it's from 1665, long before photography was a possibility. So here's a few paintings that use the technique of linear perspective. Here's another painting from the 1600s in India. We don't know who did it or even exactly where it's from, but this is, this is clearly showing that. I mean, how does this painting compare with the other ones we've seen? It feels a lot flatter. So there's a different sense of space in this one. And here's another painting from even earlier, from the 1400s, actually from the late 1400s. So this is after perspective had been discovered, because it's actually, this is from the late 1400s. That first painting we saw is from 1426. So this is actually from quite a few decades later, but this is from England, where they didn't know about perspective yet. I mean, perspective was discovered in Italy, and it took a long time it didn't take a long time, but in those days, this kind of information traveled slowly. So by the time it reached England, it was in the 1500s. So this is how typical artwork looked in the late 1400s in England. So you can see some differences, right, between these paintings and the other ones. In particular, can we see any differences in the tiles between this painting and this painting here? How do the tiles compare? What did you say?
They're flat in the first painting. They are not aligned according to the other dimensions. But in the other paintings, we can see clearly that the tiles are aligned according to the walls.
According to the...
We can see depth.
Okay, good, very good. Any other things people notice about the two paintings? Differences, either about the tiles or anything else about the paintings?
The point of view is kind of upward here, and this one's more straight.
So the point of view. So here, so where would you say the point of view is in this? From the top. And this one here?
It's from the bottom.
From the bottom. Okay. And anything else?
The checkered tiles, the tiles are all, the checks are seen pretty clearly there. Now, and the second one probably isn't very clear, but then it is big enough. But then the details are very perfectly shown in the left picture.
Yes.
Lines that are actually parallel seem to converge in the
And in the left?
They don't actually seem to converge. This is parallel there. That one they brought closer.
Okay, cool. So those are all really good observations. Interestingly, is there anything we can say about the angles or the lengths of the tiles?
there's a central point of focus there.
Hmm.
So everything converges to one point.
Hmm.
This is more an overall picture.
Yes, yes. So those are all nice observations. And it's interesting because, as you said, here, actually speaking, what do you think the tiles look like in real life that the artist was drawing in each of the pictures? In this picture, were they square? Were they rectangular? Were they all the same size as one another?
They seem to be the same size.
They seem to be the same size. And over here, in real life, do you think the tiles were the same size? Were they square tiles? Or do you think they were a different shape?
There were different shapes, I guess.
So just look at, I'm just talking about the white tiles, I guess. We can talk about.
Yeah, those are
Exactly. So even looking at both pictures, we can see that the tiles themselves, we can imagine that the tiles the artist was looking at were actually square and were actually regular. So that's conveyed in this picture, and it's also conveyed in this picture in a different way. But it's interesting because in this picture, the artist has actually made squares. So these images here, they're actually right angles, the angles here, and they're more or less look like squares. Here, if you just take one tile, one image in isolation, it's not a square. This is not a right angle, this is not a right angle, this length is different from this length. But somehow looking at the picture, we're convinced that the artist was looking at an actual proper square tiling. So somehow, despite the fact that the angles and the lengths keep changing, it actually, in some sense, this picture, the tiles look more square. Even though here, where they're actually proper squares, there's something a little odd about the layout, so it doesn't look like they're square. So there's something funny happening there. So Vermeer, he's the artist who did this one, he keeps shifting his angles and he keeps shifting his lengths, but somehow it convinces our eye that something correct seems to be happening. So, I mean, as a few people said, the parallel lines in this picture, they all, if you follow them out, if you trace them beyond the picture, they come together. They all converge at either this point for all of these parallel lines, or if you take this family of parallel lines, they all converge to that point there. So you have 2 points outside of the painting where all of the parallel lines seem to be converging. And somehow, when we see this, our brain knows that it's correct. So maybe that's not so surprising today because we're used to seeing long lines in cities when we see tall buildings, skyscrapers, or even long roads. And we're used to seeing photographs, which kind of freeze time. But in those days, neither of those were so common. So that's why it took a long time to discover this fact that parallel lines, as you continue them on forever, they actually come together, they actually converge. I mean, we can see it in photographs today, so we're used to seeing that principle. But even then, I think it's not something we stop and think about that much, so it's an interesting thing to examine. So that's what we're going to do today. We're going to look at why parallel lines converge and try and get a deeper understanding of that. So, so does anybody have an answer, just off the top of your head? If, you know, we can see that in a depiction of a scene, of a 3D scene, it looks like the parallel lines are converging. Actually, in real life, they're parallel lines. They're not really converging. But in a picture, they seem to converge. So does anyone have an explanation of why, or an idea, a guess about why that might be?
because of the angle from which you're looking at it.
Because of the angle from which you're looking at it. Okay.
Not because the line of vision, because you see things from far away, they seem to converge at a point. As in, when say you're at the end of a very long corridor, the end seems to come together towards the end.
Right.
You're observing from distance.
Right. So it seems natural. You can see that things get smaller as they go further away. And when you stand in a corridor, you see it happening. But let's see if we can get an even more precise answer to this question. So has anybody here tried drawing in perspective before? Has anybody tried actual perspective drawing? Raise your hand if you have. Okay, a few of you have, not that many. So good, today we'll have a chance to actually try it. Before we do that, I want to start with a slightly simpler experiment that I actually did just right here, yesterday evening. So the easiest thing to draw in perspective, or the thing that's most indicative of whether the perspective is working, is a simple square tiling. And luckily there's square tilings everywhere. So the floor of the bathroom next door has a nice tiled floor. So if you go to the bathroom and you look down and look at the floor, look at the tiling directly, you might see something like this. In fact, that's exactly what you'll see, because that's where I took the photograph. So this is a square tile, and together the floor is tiled with identical copies of this. So they continue and they tile the floor. So that's not very interesting as it's a simple, elegant tiling, but the photograph is not that interesting. No perspective is happening. The parallel lines are staying parallel. They don't seem to be converging. But if you tilt your head slightly, if you raise your head slightly, so instead of looking down at your feet, if you look up a little bit, then it might look more interesting. Suddenly then, some of the parallel lines will start to come together. Now, this is how a single tile looks. It no longer looks like a square, right? Now it's kind of a trapezoid. And continuing these lines, we get a tiling of the full bathroom floor. And it's a little bit more interesting than before. And if you turn your head a bit to the side now, it can become even more interesting. So now, even the other lines which had remained parallel in the previous picture have tilted, and now they also start to seem to converge. So here's a single tile now, and if we draw the grid of lines, none of them, if we just continue these lines outward, we see that they gradually come together. It's a bit more subtle than the pictures we were looking at earlier, but you can see that they're not really going to remain parallel in this picture. So this is quite a bit more interesting than the first picture. So what did we do? We started with looking straight down, then we raised our head a little bit, and then we just turned a little bit to the left. So we eliminated all the parallels that were directly parallel to our own field of vision. So here's a question. Which perspective view of the floor tiling would be easiest to draw? If I asked you now to sit down and draw one of these, which one would be easiest? The first one. Okay. And which one would be hardest? The last one. Does anyone, so most people said that this is the easiest, hardest, and this is the easiest. Sorry, this is the easiest and this is the hardest. Does anyone disagree? Does anyone think a different one of them would be easiest, not this first one? Yeah.
I think the third one is easiest.
The third one is easiest. Okay. Anybody else?
I think everything would be equally easy to draw because they're all lines after all.
That's a good point, but they're lines that are arranged in a very specific way. So not every arrangement of lines is going to look convincingly like a grid. So you have to know exactly where to place your lines, and that may not be easy. So it's interesting that one person thought they'd take a gamble and say that this is the easiest. Let's actually try these out. So maybe I didn't define easy and hard well enough. So suppose that I give you the image of a single tile. I don't give you the full tiling, but I give you a single tile, and I ask you to complete the tiling of the floor, just from that single tile, from that single image of a tile. What tools would you need to complete each of the above images? So let's start with the first image. If I give you this tile, what tools are you going to need to complete the drawing? A scale? So by the way, just to be a little precise, rather than, how many of you have studied like ruler and compass or straight edge and compass constructions in geometry? Have you ever done constructions in geometry that use a compass and a straight edge? Okay, and the straight edge, did you learn in school that the straight edge, it's usually an unmarked straight edge, meaning that you can't use it to measure. So the straight edge doesn't have numbers on it, because all measurement has to be done with a compass. That's one of the purposes of the compass. I don't know if you went over this carefully in school, but that's why we say a compass and straight edge and not a compass and ruler. Because a ruler typically has markings, which can be used to measure things, which is actually a whole other feature. That's another tool which lets us do more things. But in general, in classical geometry, they were concerned with what you can do with just compass and straight edge. So when I say tools, let's think in terms of those types of tools. Some basic tools like a straight edge, like a compass, like a ruler. So to finish this drawing, what tools would you need? So a lot of people said scale, by which let's say an unmarked scale. Let's say you mean a straight edge. So certainly you're going to need a straight edge because we have straight lines. You can't draw straight lines without some straight object to use. Do we need anything more than a straight edge, though, if we want to complete this tiling of the plane? We'll need a compass, exactly. And why do we need a compass? Because there's some measurement involved, right? Because if we can easily continue this line with a straight edge, we can easily continue this line with a straight edge, but how do we know where to mark the next point, or the next point after that? How do we know where to mark the following subsequent points? So we need a compass which allows us to take the measurement of one side and keep marking points with those lengths. So we can take the measurement of this side length, and we can mark another point using our compass here, another point here, once we've drawn that line. So using the compass, we can mark all those points. Then how do we complete our grid? How do we complete our drawing? We just take the straight edge and draw lines between those points that we've marked. So we can do a full grid that way. So it's not difficult, but it does require both a straight edge and a compass, because we have this measurement involved. So what I just said, we could extend the edges of the tile, then evenly measure out the corner points of the tiles along each of the lines we draw, and finally connect all the corners to form the grid. What about the second image? So this image, I've just tilted my head a bit, so I've eliminated some of the parallels, but not all of the parallels. There's still horizontal lines which look parallel in the drawing. So how would you complete, if I give you this tile and asked you to finish the drawing and complete the tiling, this perspective view of the tiled floor, how would you do it? So you would need a straight edge for sure. And what would you do with it first? I mean, what would be the first step?
Probably place it along the edge that's there.
Which edge?
The given edge, probably the horizontal one.
The horizontal one. Okay, so you could extend the horizontal edges using the straight edge. And after doing that, what would be the next? What could you do after that? So if you extend the vertical edges using the same straight edge, they'll eventually converge somewhere, let's say somewhere around here, right? If you extend the vertical edges of the square with a straight edge, they'll converge somewhere here. So now we've extended all the edges using the straight edge. What can we do next to complete our drawing or to go further in our drawing? What's the next step we could do? Anyone have an idea?
From that point, you can continue drawing vertical lines.
From that vanishing, let's call this the vanishing point, the point where this line and this line converge. From there, we can draw more vertical lines. But where do we draw the lines to from here? Because we don't know, we've just extended this edge, so we have a long horizontal line here, we have a long horizontal line here, and we have our vanishing point there. But where can we draw lines to from the vanishing point? So we're going to have to use our compass again. We're going to have to do some measurement. Because notice that on this horizontal line, which still looks like these still look parallel, the measure hasn't changed. The length of this side here, it's the same as the length of this tile side here, which is the same as the length here, you can imagine, and so on. So we can actually use our compass to take that length and mark off another corner point here, and another corner point here, and so on. So we can mark off a bunch of corner points along that horizontal line. And that would give us points on the horizontal line that we can connect to our vanishing point up there. So let me just, so you need both the compass and straight edge. You could extend the bottom edge, evenly measure out corner points, and extend the vertical edges to get your vanishing point. And finally, you could connect each of those corner points to the vanishing point. So you'd get something like this if you do that. But we're not quite done, because how do we get our subsequent horizontal lines? We have these two that were already there in our grid. So I shouldn't have marked those, I guess, but they were already there. But how do we get further horizontal points? Horizontal lines, rather. Any guesses? So how do we complete the grid with horizontal lines?
Use similarity. That's the base of that first. Suppose we are given that first edge.
This is, yeah, this first tile here.
Previous one.
This one, okay.
So if we're given that, we can figure out the ratio between the line on the left.
Between which one? This one.
The previous one, yeah. Actually, I'm talking about the edge.
The edge, okay.
That edge and the base edge.
And this edge.
Yeah, that is the base edge. Then we can figure out the subsequent lengths of the left-hand side by using some value.
I see. So you're going to run into an issue there, which is that these are not, you can actually when we do a perspective shift like this, we don't have similar shapes. So it's hard to see in this picture, but it's not the case that all of these different trapezoids are similar to one another. So something more is happening. It's not just scaling down. So this trapezoid is not similar to this one, which is not similar to this one. So that's a really good guess, and it's an obvious thing to try, but it won't work because we don't preserve.
The angles are the same, right? So maybe the trapezoids are not the same, but if you look at the whole triangle, it would be similar. But I guess that is not enough.
Sorry, which triangle would be similar?
Take any of the horizontal edge and the vanishing point.
Okay.
But those triangles will be similar because the base is
Oh, okay, yeah.
But that is not really helpful because we already have those paths. That just tells those lines are parallel. It doesn't tell us anything.
Yeah, so you're right. Those triangles would be similar, but the trapezoids won't be similar. So that's right. So there is, however, a very slick solution to this. Does anybody have a guess? Or should we give the answer? Do you have a guess? No. Okay. So remember, we want to draw more horizontal lines. There's,
Sir,
yeah.
maybe the vanishing point first triangle. The first triangle, sir.
This one?
Yeah.
Yeah, this triangle.
Let me take A, B, C points, sir.
So A is here,
Yeah.
B is here, let's say, and C.
C. So angle B equal to 2 times of that down edge. Sir,
Yeah.
this one, this way, shall I come in there?
So you're saying that this is A, this is B, and this is C, right?
Yeah. And down to the C is D, sir. Let me take.
Okay. Okay. Let me. Sorry. I'll actually give you. I'll give you a hint because I think we're going in a direction that might get confusing. So there's an even easier solution basically, which is that you just draw a straight line through the diagonal of the first tile. So that straight line, it's guaranteed. What do we know about its intersection with each of these vertical lines that we've drawn to the vanishing point? So it's going to hit each of those at different spots. And remember that this is a square tiling to begin with. It's a regular square tiling. So if you draw a diagonal in a square tiling, it's going to go through it's going to go through corner points. So every place where it intercepts one of these vertical lines has to be where a horizontal line comes. Does that make sense? Because this is really just coming from a square tiling. So if you draw a line through the diagonal here, every time that it goes through, maybe I'll do it for you. So if I draw through this diagonal here, every time it goes through a vertical line, it's also going through a horizontal line. So every time that this diagonal goes through a vertical line, I'm saying vertical, but it's really not vertical in this picture, it's also going through a horizontal line. So that means we have to have a horizontal line here, and we have to have a horizontal line here, and so on. And we can draw more diagonals further up to get more horizontal lines. So in this manner, we can get all of the horizontal lines without having to do any measurement. So we did have to do measurement at the beginning, so we needed a compass to measure out these points. But after that, we didn't need to do any more measurement. After that, it was just with a straight edge that we could do the rest of the work. So finally, let's look at this third tiling where we've lost all of our parallel lines. Nothing is truly parallel in the picture. Of course, it's all parallel in real life. How would we draw how would we extend this tile to a full tiling in this third image? What tools would we need? So, surprisingly, you can complete this tiling with just a straight edge. You don't need a compass, you don't need a ruler, you don't need to take any measurement. A straight edge alone is enough. So this is actually the easiest tiling to draw. And can you figure out how to do it? So let's all try this now. So we have some sheets of paper here. So we'll just quickly pass these out. So I think about half the people are almost there. So one last hint, once you have this horizon line, you can look at a third family of parallel lines, and that's going to help you solve the problem. So you look at the diagonal lines. So we know that these edges converge to this vanishing point. These edges converge to this vanishing point. But we can also draw this diagonal line, which is parallel to all the other diagonals in the tiling. And that's converging to some point here. So all of the diagonals have to converge there. So for example, then we can use this to draw a line between this point and this point, or this point and this point. And this has to be a corner of the tiling, and this has to be a corner, meaning from here we can get the other edge of this square by drawing that. And here, so now we can erase this for the time being. This is our next tile. And similarly here, we can draw a line between this point and this point. And that gives us 2 more tiles. So that gives us 4 tiles, and so on. And we can keep going like that. So it's really all about using this third family of parallel lines, the diagonals, to help us complete the tiling. So maybe, yeah, you can take another 30 seconds to finish. Sorry. Yeah, take another 30 seconds to finish. Should try it out yourself if you haven't done it. Then we'll move on. So, yeah.
Diagonal lines converge on the horizontal, on the horizon.
On the horizon, because we'll prove it in a little bit, but as a general principle, and we kind of saw it in the paintings, all lines that are parallel to the ground will converge on the horizon. So at different points, depending on which class of lines they're in, which family of parallel lines they're in. So.
I got this, I guess. So we scale up with this.
Either one, actually, it doesn't matter. Now you have everything you need. So you have this diagonal. You can just draw. So you can draw a line between this point and this point to get even more tiles. You know, you can draw between this point and this point to get another set of tiles. You can get 9 tiles that way. So.
Just one question. Is this the basis for what is called projective geometry or something?
Yes. Yeah. So.
How do you draw the just by guessing. Try to do it properly.
Okay. Okay, so I think we'll move on. So hopefully everyone, if you haven't managed to do it, you can keep the worksheet and try on the back side when you go home. Because it's a fun activity. I think everyone should try it once, just to see how easy it is. So we can the lights we can turn off. Yeah. So we'll skip that. Yeah, so basically, we can easily, I mean, if you continue this process, you can just keep continuing it, and it's actually not even that hard to get a drawing with this many tiles, because it's fairly fast. So just using a straight edge, it's quite remarkable. You can actually make a realistic perspective view of a tiled floor with only a straight edge. There's no measurement involved. So that's quite a surprising fact. So there's some natural questions to ask. First of all, why does it look so realistic? I mean, why is it that when we see this picture, somehow we can tell that the tiles, from some point of view, these tiles were the same size. It looks like a regular tiling to our brain. So that's kind of interesting. Why is that the case? Why do we just naturally have a sense that this is a regular tiling? So that's one question that at least came to my mind. Then another question is, why was this tiling, why was this view of the tiled floor much easier to draw than the other two, in that it didn't require any measurement, it didn't involve the compass or any other form of measurement, it just involved connecting points with your straight edge over and over. So it actually was quite a bit easier in that sense. So why was this one easier, even though it's a much more visually interesting image? So we won't answer those right now, but you can think about them. Maybe we will talk about the first one a little bit though, in terms of how can we tell that these tiles are actually regular? How can we tell that this is a view of that same very, very regular square tiling we saw at the beginning from a top bird's eye view? So in particular, what do these images have in common? Obviously, when we change the viewpoint, a lot of things change. The angles change, the distances change. So what stays the same? So something has to stay the same because we can tell that it's the same grid. But what is it that stays the same as we move the camera around? So straight lines remain straight. Anything else that stays the same besides straight lines? Diagonals remain diagonals. Another way of saying that is that intersections remain intersections. So if here two lines intersected, when we change, the lines stay lines, and if the two lines intersected here, they continue to intersect in the shifted image. What about parallel lines? Here we have parallel lines. Here, well, they're still parallel lines, but they converge on the horizon. So parallel lines either remain parallel or meet at the horizon. When we went from the first picture to the second picture, the horizontal lines remained parallel. The vertical lines started converging at the horizon. Then when we jumped to the third picture, even those horizontal lines started converging on the horizon. So that's interesting. Let's see what we can make of that fact. So let's look at the horizon a little more carefully. And let's pretend for a minute that all those vanishing points, like in your picture you drew those 3 vanishing points, but let's pretend, and in general you could imagine that all the other points on the horizon are also vanishing points of other families of parallel lines. For example, you could draw a line take this tile here, you could mark, if you have a point that's 1/4 of the way up and a point here that's 1/4 of the way down, you could connect those with a line. That'll be a line that's not parallel to any of the other lines we've talked about. And you could do that for every tile, and you get another family of parallel lines. And those would also converge to some fourth vanishing point. So any point on this horizon is the vanishing point of some family of parallel lines. So let's pretend for a minute that all these vanishing points, all these points at infinity, that's the other term that mathematicians use, all of these different points at infinity are not just imaginary, but are that they actually exist, okay? Maybe they don't exist on the plane, but they exist somewhere, somehow. They're not just in our imagination. And let's imagine that the horizon is an actual line containing all of those points at infinity. So the horizon becomes a line at infinity. So let's just imagine that for a second. Now, in that scenario, everything suddenly seems very elegant, even more elegant than the coordinate Euclidean geometry we're used to. Because any 2 points determine a line, just like we're used to seeing in Euclidean geometry. But now, any 2 lines intersect in a point, right? Any 2 lines are either parallel, in which case they'll intersect on the horizon, or they are not parallel, in which case they'll intersect off of the horizon. Like this line and this line intersect off of the horizon. So it's very elegant, except that I'm ignoring the fact that some parallel lines actually look parallel. So we may have to turn a little bit. For example, these horizontal lines still look parallel here. But if we turn a little bit, then we see a point at infinity where they converge. These formerly horizontal lines suddenly start to converge if we turn a little bit. So it's almost this very elegant situation. So that begs the question, can we actually define a geometry? Can we actually define a system of points and lines and planes that intersect and that contain one another? Can we design a system like that such that any two lines intersect in a point and any two points determine a line? So can we design something that's even more elegant than the Euclidean geometry that we're used to? And if we can do that, maybe we can model our vision on that, because that's almost how our view, our actual vision, almost how perspective drawings behave. So if we can find a geometry, a system like that, maybe that'll also tell us something about how our vision works. So let's assume that we can do that. I won't show it just yet, but let's suppose we can actually design a geometry like that. And let's call that structure a projective plane. So we'll give a few axioms that the projective plane should satisfy, and then we'll see if we can actually cook up a projective plane which satisfies them. So the axioms are simple. Any two points should be contained in a unique line. That anyway we're used to, that's very intuitive from coordinate geometry. Any two lines should intersect in a unique point. That's what we were just talking about. That's what we'd like to have happen so that we can model our vision. Our vision is basically like this. And finally, this one is not as intuitive, but it turns out to be important. We want to have at least 4 points, no two of which are in a line, meaning that there's enough lines for the geometry to be interesting. Basically, this corresponds to how in the drawing you did, or in the drawings we saw, we have an initial tile, which we can then use those 4 lines that determine our initial tile. We can extend them and we can make more and more tiles. So this basically shows that our geometry is interesting because there's enough points and enough lines that we can do interesting things. So we should have at least 4 points that are not, no 3 of which are collinear. In other words, we should have a quadrilateral of some sort. That's really what this is saying. So if we can find something that satisfies these, it's known to mathematicians as a projective plane. And so the question is, can we find something that satisfies them? Is there such a thing as a projective plane? And the answer is yes. There are actually many different projective planes that we study in mathematics, but there's one that's the most basic and the most natural and the most common, which I'm going to give a recipe for right now. So let's take R3, standard Euclidean space, and let's fix a point in R3. Let's take our points in our projective plane to be lines through A in R3. So we have a point fixed in R3, and we'll take our plane to be all the lines that go through that point. And we'll take our lines to be planes through A in R3. So this is getting confusing, I guess, because I'm using points and lines to mean 2 different things. So really what I should have said, let's take our projective points to be lines through A in R3. And let's take our projective lines to be planes through A in R3. And finally, let's let our projective plane be the set of all lines through A in R3. So we'll call this projective plane RP2, the real projective plane. This is how it's typically denoted by mathematicians. And the question is, does it satisfy our axioms? So let's recall the axioms. Any 2 points should be contained. So maybe to simplify this point A, let's just think of that as the origin in R3. So when we're talking about projective points, we're really talking about lines through the origin in R3. So a line through the origin in R3, we'll call that a projective point. A plane through the origin in R3, we'll call that a projective line. And the set of all lines through the origin, we'll call that the projective plane. So this is a bit of a stretch of the imagination. So I think with a picture, it'll make more sense. But let's check quickly if it satisfies our axioms. And then I'll show a picture. So first of all, the first axiom is that any 2 points should be contained in a unique projective line. Any 2 projective points should be contained in a unique projective line. Well, a projective point is a line through the origin. If I have 2 lines through the origin, those uniquely determine a plane through the origin. And a plane through the origin is a projective line by my definition. So it satisfies this. Any two lines through the origin are contained in a unique plane through the origin. So that first axiom is satisfied. The second axiom is that any 2 lines should contain a unique point. In other words, any 2 planes through the origin should contain a unique line through the origin. And that's true. If you take two planes in R3 which go through the origin, they're going to intersect in a unique line through the origin. So any two projective lines will contain a unique projective point. So that's why RP2 satisfies this. Finally, the third axiom is a little weird, but RP2 satisfies this as well. There have to exist 4 projective points, no 3 of which are on a projective line. In other words, there have to exist 4 lines through the origin, no 3 of which are in a plane through the origin. And we can just take these simple vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 1, 1. Each of those vectors determines a line through the origin, and no 3 of them lies in a single plane through the origin, right? 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1. If you can picture those, there's no way that 3 of them will sit inside a single plane. They'll always, so the 4 axioms will be satisfied that way. And the fact that RP2 satisfies them is not just a fluke. It's really because there is something about our vision that's captured in this definition of the projective plane. In particular, it captures the idea of viewing this floor with an all-seeing eye based at a point A. So when you're looking at the ground, any point you see on the ground, what you're really seeing, your eye is actually picking up on a whole line of sight. There's a line of light that connects the given point to your eye. And in your vision, that line of sight becomes a point. So when what you're seeing is actually lines through this origin, through A, your eye is is based at A and can see in any direction, let's say. Then any image you make is going to be made up of different points, different pixels, and each of those pixels is going to come from a full line that extends from your eye to some point in space. If I'm looking at the clock there, and I'm looking at the very tip of that minute hand of the clock, there's really a line from that tip of that minute hand going to my eye. That's not okay. Suppose I'm looking at this speaker here. There's a Bose speaker, and there's a B on it. And I'm looking at the letter B. There's a line going from the letter B to my eye. And that line is registering as a point in my image, in the picture that I'm seeing. And I'm seeing that corner of that letter B, but really there's a full line from my eye to that point. So each line becomes a point in your image. So really we can think of the lines through A as lines of sight, which connect the eye to the points it sees. And all the points on the tiled XY plane correspond to lines through A. So on this XY plane, which has a grid on it, I have a point here, and that point corresponds to this line connecting this point P to the point A where my eye is. In fact, all of the points on the floor correspond to different lines through A. So the different lines through A are all hitting the floor at different points. And are there any other remaining lines through A besides the ones that correspond to points on the floor? So I think it's a bit of a vague question, but actually, what we can think of what we've done as in the following way: we've extended the floor to a projective plane by adding some points at infinity. So there's horizontal lines through A which never hit the floor. And there's a horizontal plane through A as well, which never hits the floor. So there's horizontal lines through A. Those are projective lines which are never hitting the floor. So those are really like points at infinity. And you can actually see here, this line here on the floor, as I look along it, these are all real points which correspond to which hit my eye at various different projective points. There's various lines through A which are going to hit this line on the ground further and further along it. But as we keep going off into infinity and looking along that line on the floor, these lines of sight are going to converge to a horizontal line. And that's going to be that's really like a line at infinity. So as I look along this line and keep looking further and further along, my lines of sight are going to converge to a horizontal line. And that horizontal line in my projective plane model, it's still a point in the real projective plane, but it's now a point at infinity. So the points at infinity are really the horizontal lines through A. And all together, they create a line at infinity, which is the horizontal plane through A. So a perspective drawing or even a photograph is simply capturing the points of RP2 as points on a fixed picture plane. So going back to my initial picture I took of the ground, if you imagine this being the tiled bathroom floor, that XY plane, or this plane that's below let's say it's z equals -2. I'm looking down at it, and my picture plane is parallel to the floor. So when I take a photograph here, my picture plane is parallel to the floor. So, and all of the different points on my picture are coming from the points where my line of sight pierces the picture plane. So there's a point here on the floor that I'm looking at, but in my picture, I'll end up with a pixel right there. And if I'm looking at this point, it'll pierce the picture plane somewhere else. So I'll resolve a picture that way by getting different pixels from different places. Similarly, similarly, the second one where I turned my head up a little bit, rather than looking straight down, I looked up. Now my picture plane is vertical. I'm still looking at the tiled floor, but because it's vertical, not all the lines will look parallel. In particular, these lines that are going from left to right, they're not going to look parallel in my picture plane. They're going to converge as we go further and further out. And we'll prove that in a second. We'll see exactly why that is in 1 second. So similarly, after I turned my head a little bit, I'm just turning my picture plane. And now none of these grid lines are going to look parallel when they pierce my picture plane. So I think there's an advantage to looking at those pictures and trying to understand it visually. But we can also understand the same principle algebraically using homogeneous coordinates. So let's actually say that A is the origin. It's 0, 0, 0, like we were saying earlier, but let's pin it down. And we can use linear algebra to actually handle computations involving the real projective plane. So remember that a line through the origin is determined by any point outside of the origin, and and consists of all of the points which are scalar multiples of that point, where t runs through all the real numbers. So for example, if you take the point 1, 2, 3, and look at t, 2t, 3t, and let t run through all of the real numbers, you'll get a line through the origin. Or if you take any point, a, b, c, and look at all of the points ta, tb, tc, where t runs through all the real numbers, you'll get a line through the origin. So it's easy to check that we can form an equivalence relation where we say that abc is related to any scalar multiple of abc by a non-zero scalar. And it's easy to check that's an equivalence relation. So we can denote that equivalence class a colon b colon c, and we call that homogeneous coordinates. So when we write a colon b colon c, we really mean the line that's spanned by the vector a comma b comma c. So that's really what this notation means. So this is a common notation. It just means the line spanned by the vector a comma b comma c. And this is a good way to refer to denote points in RP2 through homogeneous coordinates, because a point in RP2 is a line through the origin. So we just need to, we don't have to worry about which point we pick on that line. If we write it this way, we just mean we mean that whole line that's spanned by the vector ABC. So we're going to use homogeneous coordinates now to prove a few basic facts. In particular, we'll prove that parallel lines actually converge. We'll see why they actually have to converge. So I want to quickly go back to what we were talking about at the beginning, which is drawings and paintings. So far we've just been talking about tiles which are stuck on the ground, but obviously the paintings we were looking at also have lines and objects and shapes that are not on the ground, and still perspective applies. So we can actually depict any shapes using the same principle that parallel lines converge. It doesn't have to be tiles, it doesn't have to be things on the ground. For example, we can easily draw boxes or houses or any other shapes. So, so very quickly, I'll just show that the same idea of convergence still applies when we look at things that are not stuck to the ground. So in general, to draw a perspective drawing, you can draw your horizon line, and you can give yourself a couple of vanishing points, and then it's very easy to draw a cube. You just keep your vanishing points in mind. So in this case, this is one vanishing point. This is another vanishing point. Keeping those in mind, I could, for example, you could draw a cube with a corner here. So in this direction, it has to go towards this vanishing point. In this direction, it has to go towards this vanishing point. Then, in this case, to simplify life, I'll make the vertical line actually look vertical. And this vertical line actually look vertical. And this vertical line also, I'll make it look vertical. Now, here, again, this edge has to move towards this vanishing point. So we'll get something like that. And here, again, we'll have convergence to that vanishing point. So we get a cube that way. And similarly, you could draw a cube anywhere, really. So if you drew a small cube here, it would go towards this vanishing point from this corner, towards that vanishing point from that corner, and so on. So in this way, you can keep drawing cubes or buildings or anything else, and you can very quickly and easily draw a scene which is not just a tiling, but involves multiple levels, multiple heights. So, yeah. So there's nothing special, and moreover, in this case, I'm using the same horizon line because all of my families of parallel lines, even these ones up here, are parallel to the ground. But the only thing that's special about the horizon line that I drew is that all lines parallel to the ground converge to that. But even lines that are not parallel to the ground will converge. So any two parallel lines will converge to some point. And if they're not parallel to the ground, they'll converge to a point which is not on that horizon line, but on a different horizon line. So we can have vanishing points off of the horizon as well. So I guess we can turn off the lights again, sorry. So we see this when we look at an actual painting. We see that there's vanishing points. There's usually a horizon line where the lines that are parallel to the ground converge to. So in this picture, if we draw the edges of this tabletop, we'll find a horizon line that is approximately here, somewhere here. But there's other lines that we can draw. For example, if we draw the diagonals of these windows, those are not parallel to the ground. And those, if we draw this diagonal, and we draw this diagonal, and we draw this diagonal, those are going to converge to some vanishing point down here somewhere. And you can just see, do you see any other families of parallel lines in this picture? There's actually many. Which one? Sorry, the ceiling, yes. So the ceiling, yes, that's another good family of parallel lines, but it'll also converge to the horizon because it's also parallel to the ground, right? The ceiling is parallel to the ground. So these lines on the ceiling, they're going to converge to a different, they will converge to a different vanishing point, which is also on that same horizon line. But are there any more parallel lines that you see? The shadows of the window. So that's a good example, except that if you've seen the way that shadows come out of a window, even though these ones are parallel, but these are no longer parallel. So this and this are actually not parallel. When you see light coming through a window, the lines are no longer parallel to each other in real life. So those won't go to the same thing. But Okay, anyway, I'll leave it as something you can look at on your own, but it's a fun exercise to look at some of these paintings. This one is by Dürer, Albert Dürer, who is he also lived around the early 1600s is when he painted this, and he was a master of perspective soon after it was discovered. I mean, about 100 years after it was discovered. So, but if you look at old paintings, you can see that they really had a sophisticated idea of it, because a lot of the parallel lines don't converge to the horizon. They go in all kinds of other directions. So next time you see a painting in perspective, an exercise you can play is, can you find the different vanishing points? Can you find the horizon line? And can you find any vanishing points that are off of the horizon line? So the last thing that we'll talk about, though, we have a few more minutes, is why do parallel lines converge? So we've been using that as a fact, and we've seen that it works really well in creating a realistic drawing. But why is that the case? So the answer, it's not hard to show using homogeneous coordinates, but it's also something that we can just see by, okay, I guess this is not a straight line. So for example, if you take any straight line, like this edge of the stage, from where I'm standing, actually, I should do this from where you're standing. So from where you're standing, do you see any straight line that's going off into the horizon? The problem with, this is not, the edge of the stage is not really straight. And the others are not very long. So I think this is roughly a straight line, right? The edge right here. Is it curved or is it straight? This is straight. Cool. So if you imagine that you're standing facing the stage, and maybe at some angle, so you're looking in this direction at this line. As you're looking at it, what's happening? If you imagine it extending infinitely far off, as your eye is following it, what's happening? How far, in your image, in your picture, is that line going to go on forever, first of all? In real life, let's assume that this line actually goes on forever. And let's assume we have really good vision and that there's nothing blocking our vision. So in theory, we can just keep looking at this for another 100 meters or 1,000 meters or 1,000,000 meters. We can look at this line as it goes off into space as far down as we want. So let's imagine that we're standing here and observing this line as it goes on and on and on. So in our picture plane, what are we going to see? Will this line go on and on forever? Will we have to make an infinitely large picture plane in order to capture it? Or if not, why not? What will happen? Yeah. No. So at what point, as I'm looking, assume that like my eye is giving this laser, I'm looking. I'm turning my head as I'm looking to keep following this line. But at some point, would I have turned my head too far? Even though the line goes on forever, at some point, would I have turned my head too far? At which point? As I'm looking. I mean, it's hard to see because we have all this stuff blocking us, but at this point, am I still going to intercept that line if I'm looking down here? Am I still going to intercept that line at some point? And now am I still going to? And now am I still going to? At some point, I've gone too far, right? Now there's no way, even if that line goes on forever, I'm never going to see that line if I've turned my head this far, right? So when have I gone too far? When have I turned my head too far and there's no longer any hope of me seeing that line? Even though I have perfect vision, even though it goes on and on forever, even though there's nothing blocking me, when have I turned my head too far? So when I move too far to the left, and how do I know I've gone too far?
At one point you're standing back.
Yes, when my line of sight is parallel to that line. So up until my line of sight becomes parallel to that line, I'm all good. I can still, eventually my line of sight will hit this, somewhere really far away. Maybe it'll be a mile away when I'm really close to this parallel line. But when I hit the parallel line, then I'm not going to see it anymore. So basically, as I'm following this line along, my line of sight converges to a line of sight at infinity, basically. So it's converging, my lines of sight as I'm looking along are converging to a line of sight which is parallel to this. And that line of sight which is parallel to this is never going to see this. But in my picture, if I'm also painting or taking a photograph or drawing what I'm seeing, the image of that line isn't going to go on and on forever. It's going to converge, and the point it's going to converge to is exactly this point on my picture plane. Maybe my picture plane's here, so I've looked and looked and looked. Now my line of sight is parallel to that line, and my picture plane is going to capture that point right here. So that's going to be the vanishing point of that line in my image. But what if instead of this line, what if we'd taken another line which is parallel to it? In particular, what if we'd taken, instead of this edge, what if we'd taken this edge? You see, there's also an edge, parallel edge, which is on the back side of that pillar, right? I mean, basically the top of the pillar. If I'm following that line along instead, what's going to happen? I'm following it, following it, following it, turning my head, turning my head, turning my head. Then, at some point, I've gone too far. What point is that? It's when I'm parallel to this line. So the vanishing point is going to be here, but that's the exact same point. So, because these two lines were parallel to begin with. So it's when there's only one line from my eye which is parallel to both of these lines. So they're going to have the same vanishing point. So when they finally converge, it's going to be to the exact same point. So that's the basic reason why parallel lines converge. Another explanation we can give using homogeneous coordinates, just to show that these are actually useful, we can suppose that we take any point in R3, P, and let's let V be any vector that's not parallel to the plane Z equals 1. So let's say that my picture plane again is Z equals 1, and I'm looking down from there, down through it, and let's just take any point in R3 and any vector not parallel to that plane. Sorry, I'm looking up, let's say. So Z equals 1 is up here. And I'm looking up, and I'm taking any vector not parallel to the plane and any point. So as we're looking further and further along the line, we can denote the line this way, P plus TV, as T is a real number, for T being spanning all real numbers. That's a way of denoting a line. Now at time T, as we're following this line with our eye, we're going to see the point, we're going to see this point in the projective plane. So I'm writing in homogeneous coordinates here. P1 plus TV1, P2 plus TV2, P3 plus TV3. The reason I'm using homogeneous coordinates, and the reason that I'm talking about us doing this in the projective plane, is because, remember, when we're seeing something, anything we see, our line of sight is a line, and it's starting at the origin, which is my eye. So at any point time t, we're actually seeing a line's worth of information. I mean, what we see is actually a full line. So at any time t, this thing here is a line, represents a line. Really, it represents all scalar multiples of this vector. But we can rewrite that, because remember, in homogeneous coordinates, we can scale all three coordinates simultaneously without changing the class of that coordinate, the class of that point. So without changing the point it represents. So by scaling, by dividing by this last quantity, we can rewrite this homogeneous coordinate in this way. P1 plus TV1 over P3 plus TV3, P2 plus TV2 over P3 plus TV3, and 1. So now, the reason I've rewritten it this way is because now it's in my picture plane. Now I can see which point it is in my picture plane, which is Z equals 1. And as t goes to infinity, meaning as I'm looking along the line further and further, what does this converge to? Well, as t goes to infinity, we lose the p's, P1, P3, P2, P3. And this becomes V1 over V3, V2 over V3, 1. So that's independent of the point P that we started at. So we end up with a coordinate on my picture plane which is independent of P. So this point, V1 over V3, V2 over V3, 1, is the vanishing point in my picture plane Z equals 1, not only of the line L, but of any line parallel to it. Because all that mattered was V. All that mattered was the direction of the line. The initial point didn't matter. So all the parallel lines converge to the same vanishing point. So that's it for the talk today. That's hopefully that explains why parallel lines converge, and gives you, something you can do when you just have a straight edge and some time on your hands. So hopefully you can play with this a little bit more. If you're interested in these topics, most of this material for the talk was from a book by John Stilwell called The Four Pillars of Geometry. And I really I really just scratched the surface of a bunch of topics that are there in that book. So if you're interested in projective geometry, which is all of the geometric properties you can get just from those axioms of the projective plane, which is surprisingly a rich topic, there's a lot of theorems and a lot of things one can prove, then that's one direction you could go. Another direction is just to study the real projective plane. That's a very interesting surface, and it's the starting point of many topics in geometry and topology. Finally, the cross ratio is an actual quantity which is preserved under transformations, these perspective transformations. So there's a reason why we can just naturally see, why our brain naturally knows that all of those images we are seeing are actually coming from a proper square tiling, which is that all of those have the same cross ratio, and our brain is somehow trained to pick up on that. So a cross ratio is a ratio of ratios. We don't have similar shapes. Somebody thought they were similar. They're not similar, but the ratio of the ratios is fixed. So I won't go into details because there's no time, but it's a very interesting topic, and it has a lot of applications in geometry. So the cross ratio is an actual physical quantity that's preserved, and you can measure it by taking the ratio of the ratios between points when you do a transformation of a line through this perspective transform. So, but that's it for the talk, and feel free to ask questions after the talk, because I think we're out of time.